Welcome to the tutorial about the wear analysis inside PrePoMax. Now we'll take a look at a simple problem of a pin on a plate. The assignment is to determine the wear depth h on the plate. Plate is shown with a number 1 on a figure 1, and then we have a pin which is number 2 on figure 2, and this pin is pressed to the plate using a force of 200 newtons. This pin oscillates to left and right with a frequency of 1 Hz and an amplitude of 10 millimeters for 10 seconds. This means the pin is about to do 10 movements to the right and back again. For the computation of the wear depth, use the Arcard's wear model, which is based on the Arcard's equation. This is the only model that is currently supported by PrePoMax. Both parts are made from steel S235 with Young modulus of 210,000 megapascals and a Poisson's ratio of 0.3. Material surface hardness for this material equals 100 megapascals, while the wear coefficient equals 0.001. The contact friction coefficient equals 0.3. So we will load this geometry in PrePoMax. We will consider that this model is symmetric and we will use only 1/2 of the model for the analysis. Then we will mesh the model, apply the loads, boundary conditions, and first try one oscillation or one movement of this pin to see how the model should be set up. And then we will continue and increase the number of movements of the pin to final 10. So let's start in PrePoMax. First, we'll load the model that we will need for this assignment. So let's select File New first to create a new model. We'll use a 3-dimensional model space and a unit system with millimeters, tons, seconds, and degrees Celsius centigrade. So just confirm by OK. Now we'll use File Import to find the geometry of pin on a plate. This geometry is saved inside PrePoMax folder in the subfolder called Models. So just open up pin on a plate. As already mentioned, we'll analyze only 1/2 of the model. It's a cylindrical pin on a plate, and both of the geometries were a little bit split. This was done in order to improve the homogeneous creation of the mesh, because in this case we'll use very coarse mesh just to show how this functionality in PrePoMax works, and the results, final results, will not be very accurate. So first of all, we'll rename both parts. The first one is called the pin, and the second one is called the plate. Then we'll set up general meshing parameters, selecting both of the models, right-clicking, meshing parameters. We'll use very coarse mesh, 5 millimeters, the largest element size. Now we'll decrease the number of elements per edge and curvature to 1, and we will definitely not use second order elements, which are the elements which are more precise. We'll use linear finite elements, which are very approximate, but still good enough to show the functionality for this case. Confirm by OK. In the places where the contact will occur, we'll improve the mesh a little bit. So let's double-click Mesh Refinement, add the first mesh refinement on the pin, and this is like the bottom surface of the pin where the contact will occur. We'll use finite elements with a size of 1 millimeter. OK and New, and then we'll select the bottom edge, like the internal edge of the pin, so only the internal small two edges, in order to further improve the mesh quality to reduce the mesh element size to 0.5 millimeters. Now we'll continue this procedure also for the plate. We'll select outer two surfaces and assign an element size of 1 and continue with the internal 4 surfaces where we will assign a finite element size of 0.5. Confirm by OK. Select both models, right click and create the mesh. Now the mesh is very coarse. We can take a look at tools and query and assembly to see that number of nodes is only 619. This is very low, but again we need a fast model to check the functionality. Now the next thing that we'll do, we'll create the material. So right click materials, create, or double click, enter the name as 235. We'll use first elastic properties, double click, and we'll add 210,000 megapascals for Young modulus. For Poisson ratio, we'll use a value of 0.3. And then we'll add parameters which were added in this version. These are slip wear parameters for material. And then here we have to input the hardness of the material, which is equal to 100. If we remember the assignment, so we have a 100 megapascals hardness and a wear coefficient of 0.01. So 0.001, sorry, 110 more. Confirm the material by OK. Now assign a section, double click, select both parts and enter the name for this section like a solid, and it's made from material S235. Just confirm by OK. Constraints. Now how to move the pin in the oscillating manner. We'll create a reference point at the top, connect the reference point with the top surface of the pin using a rigid constraint. So first of all, create a reference point by double clicking. We'll name it as RP for reference point on the pin. We will not select the coordinates for this point, but we will try to define it using circle in the center circle by 3 points. So we'll select 3 points using on the top surface, and the software will compute the circle center, and we can see that the z coordinate is actually something on the power of -16, so it's actually equal to 0. Just round the number to 0. Confirm by OK, and we'll make additional constraint which will be of type rigid body, so we'll call it rigid pin. The reference point is already selected, and we have to select the top surface of the pin for the connection. Confirm by OK. Now the following thing that we need to do is to define contacts. So let's first define the surface interaction. We'll just leave the default name, or maybe just call it pin to plate, and add a surface behavior. Now usually a hard setting is quite good, or you can select any other setting for the behavior of the contact, but in this case because we have a very coarse mesh, the stress distribution using a hard contact will be not good enough, because the stress will be so like contact pressure will concentrate only on individual points, and we need a more smoother stress distribution in order to show the wear analysis, and that's why we'll use a linear surface behavior, and we'll reduce the pressure over closure slope from, I think those are 10 millions. We'll reduce this value to 100,000. This is usually not a very good approach, but in this case to show how the functionality works, it will be good enough. And we'll add a friction properties, and from the assignment we saw that the friction coefficient should be equal to 0.3. Confirm by OK. Now contact pairs, we'll do it by hand. Contact pair could be called like pin to plate, and we'll use a surface to surface contact without adjustment. So we don't want adjusting the position of the nodes at the beginning. We have to select a master region for the surface. Now, in terms of wear simulations, only the slave side of the contact can be worn out. So for this reason, we have to select the plate as a slave surface or slave part of the contact, and we have to define the pin for the master. So we'll select the bottom surface of the pin as a master surface, and then we'll select on the slave side, we have like here 4 surfaces, one connected to the other. I will select all 4 of them in order to have a continuous contact surface. Confirm by OK. How will we move the pin? Because the frequency of the movement is 1 Hertz, so it will take 1 second for the pin to go to the right and back again. So we'll do that in one simulation step, and in order to define such a motion, we'll need an amplitude definition. So double-clicking amplitudes will open the editor for creating amplitudes, and the only one at the moment which is available is tabular, which requires you to enter all the amplitude points in dependence from time. In this case, we are dependent from time. For dynamic simulations, there is dependence on the frequency. So in this case, don't confuse the frequency of the assignment with this frequency here. It's not the same. So this curve could be any kind of curve. It could be just a bilinear curve that we will do, or it could be also a sine wave or something else. It's not exactly described in the assignment, but because we can enter the sine curve, we would have to compute in front. I didn't do that. I will just use a very simple bilinear curve. So at time 0, the position of the pin should be here, so the amplitude is also 0. At half the simulation time, this is 0.5 seconds, the amplitude should be equal to 1. And at the final time of the steps, this is after 1 second, the amplitude should be 0 again. We can select all these data points and plot them to see how this amplitude looks like. So from the beginning, the amplitude will linearly increase up to the value of 1 and then decrease again towards 0. Confirm the amplitude by OK. Let's go to step, create a first step, and the first step will be a static step. So we will do the analysis in 2 steps. In the first step, we'll apply a load in order to create contact between both parts. And then in the following step, we will move the pin to the right and back again. So the first step will be static step. We'll turn on the nonlinear effects of large displacements because later we will deal with larger displacements, so this switch should be turned on in any case. And the rest of the settings will be as defaults. Confirm by OK the creation of the step. I will a little bit collapse the tree in order to see the step settings better. Now what we'll add boundary conditions. Now we know that the pin is moving, but we do not know explicitly that the plate is fixed, but we will assume, of course, that one of the parts should be fixed in order for the contact to work. So we'll use a name fix, and we will fix the bottom surface of the plate. With OK new, we'll add an additional constraint. We'll put a constraint on the reference point of the pin in order to prevent the pin from moving in any other direction than in the Y direction in the first step. So the only direction of movement which will be free for the pin will be in the Y direction. So this is up, down on my screen. So I will add displacement rotation boundary condition. I will call it pin. The region that I will select is actually not possible to select a reference point. So instead of selection, we have to select a drop-down menu and select the reference point by name. So this is the one, reference point pin. And now I have to, as I said, fix all degrees of freedom in the rotational sense and in translational sense, and I will just leave the displacement in the Y direction free. So this pin is able to move only up and down. Confirm this pin boundary condition. And because the component is symmetric, I need a symmetry boundary condition on the symmetry planes. Now, because the top part of my pin is connected with a rigid connection, this edge that I'm showing, so the top symmetry edge of my pin is already fixed, so the boundary conditions are already defined. I should not add additional boundary conditions on the rigid top surface. So in order to create a symmetry boundary condition, I have to select all the nodes on the symmetry plane except the nodes on the top plate, which are inside a rigid connection. So I will create a node set. So I cannot do it directly. I have to go through the node set. So the node set that I will create, I will call it symmetry. And using a surface angle setting, I will select all the nodes on the symmetry plane. And then using the control key, and edges, I will remove all the nodes which are already in a rigid connection. So in this case, I created node set, and now I will create a boundary condition for the symmetry. I will select displacement rotation. I will call it symmetry. Instead of selection, I will choose an option to select node set, and this is the only node set that I have. So node set symmetry, and I have to constrain the translation in the Z direction. So I will select 0 millimeters in the U3 setting, or degree of freedom. I will confirm that by clicking on the OK. And I will also hide this boundary condition. So I'll just right click, hide it, because it shows all the nodes. So the last thing that I have to do now, after defining all the boundary conditions, I will define the load. Now remember, there is a load of defined 200 newtons on the pin, but because we are only assuming or analyzing 1/2 of the component, we will use half of the force. So we'll assign a concentrated force. I will call this force. I will put this force on the reference point. So this is reference point pin, and the direction should be in the Y direction, and it should be equal to minus 100 newtons. So this is half the force. Confirm by OK. I think the model is prepared for the first analysis run. Only one step is defined at the moment, and this one step defines only the force towards the plate. So just run our model and see what happens. After the simulation is finished, let's take a look at the results. Now let's first set up some post-processing settings. I will open the settings by double-clicking the legend, go to post-processing. I will first change the deformation scale factor to true scale, I will turn off undeformed model visualization. So I'll select option no, and I will also disable the maximum value label. So apply, and okay, now I think it's better. And what actually happened, if we take a look at the single increments, slowly the pin was pushed towards the plate. We can see the Mises stress between the plate and the pin. If we hide the pin, we can see now that here it's quite a larger area that's affected, and as I mentioned, the contact definition at the moment is very, very soft. So this, we know now that our setup for the first step is working. We'll continue with step number 2. And in this step, we'll try to move the pin to the right and back. We'll add another step. So double click the steps setting. We'll select now, in this case, a sleep wear step. It's actually the same step as a static step, only that the software will compute the wear variables only in this step. So you cannot use static step and compute wear. You have to use a static wear step and tell the software to compute the wear variables. So I will call this step step wear. And I will change the incrementation because for the wear analysis, it's very important that the pin is moving along a direction very slowly so that the surface and the contact pressure slowly moves from one region to the other. There should be no larger leaps, so that in the first increment we will have contact pressure here, and the next the contact pressure will be computed here. So that is why it's important to select smaller, or let's say small enough time increments in order to have a smooth motion of the pin, in order to have then also a smooth distribution of contact pressure. So I will use a setting of 0.2, 0.02, and this will at the end create like 50 increments, and so 25 increments moving to the right and 55 increments moving back to the origin. Now let's try it with this setup first. We have to change the boundary condition, so we have to apply a movement to the pin, so everything else remains the same. So in step wear, select the pin, and what we'll do, we'll enter the value for the X displacement. So at the end of when our amplitude is the highest, the displacement in the U direction should be 10 millimeters. And we'll select, instead of a default ramp amplitude, we'll select a tabular amplitude that we defined, which will push the pin at a time of 0.5 seconds to the right position, and then at the time of 1 second it will push it back to the beginning. So confirm these settings by OK. Right click the analysis and run the analysis again. Now we just got a warning that for the moment, despite that we are using a sleep wear step, all the sleep wear variables will not be computed because our model is not defined as a model where a sleep wear is taking place. This we will do later. So for now, just confirm by OK to see if this analysis is working. After the analysis is finished, we can take a look at the results, and what we'll we can see is maybe we can plot like a Mises stress, open up the animation toolbar, and with using option more and time increments, we can now see what the simulation is about. So at the beginning, we have a compression of the pin towards the plate, and then the pin starts to move to the right, and it moves back to the beginning. So now we know that our simulation is good in terms of kinematic movement, and it behaves as we expected. We got additional output, field outputs in this case, and this is the contact field output. And here we can take a look, for instance, at the pressure. I will hide the pin for the moment. We can see that the pressure distribution is not very smooth. It's very coarse, but it's good enough for our test case. So it's important that this stress, the contact stress, doesn't jump from one place to the other. It's important to have like a smooth transition from one node to the other. Of course, the values are not very accurate, but they are smooth in terms how they change. Now, we have everything prepared, and we can run our first analysis with evaluation of the wear. What we have to do as the last step is go to the model, edit its setting, and instead of model type and general model, select the sleep wear model. Here, the first settings that we'll use as default is results all. That means that all the increments that are computed will be saved as results. This is good if you want to see what's happening with your model, but at the end, when you are running a larger number of cycles, so we'll try to repeat this one simulation multiple times, the number of results will drastically increase, and it could cause problems. And that's why you can, instead of all, select also that you only would like to save results of sleep wear steps. This is the step number 2 in our case. Only the last increment of each sleep wear step, or only the last increment of the last sleep wear step. So this is the final position after your one simulation, one cycle. For the moment, I'll keep all the results. I will keep also for the start number of cycles as 1. So I will just repeat one oscillation of the pin. Now, mesh deformation, I will come back to these settings later, which I will be able to explain a little better. And I will explain the enforce zero boundary conditions setting. Here the definition or the explanation tells you that it's something that you should use for the case where you are having a symmetric model. So in terms of symmetric model, the wear analysis is doing something like that after one cycle of the simulation is complete, the wear parameters are computed, and also the wear depth is computed. And after the simulation finishes, so after one cycle is finished, the surface, which is like defined as a slave surface, will be deformed using the depth wear. So the depth of the wear, and that means that the nodes on the surface which were in contact with a pin will be moved towards the material. So they will be moved towards the material. Now in this case it could happen since here we have a symmetry boundary condition, that those nodes could go out of the symmetry plane. So they could be moved also in the z direction, and we don't want that, and that is why we here enforce the zero boundary condition. So let's confirm this setting by OK, and let's try to run this simulation, and we will get a warning to overwrite our previous results, and additional warning that at the moment we don't have any contact history outputs. And if we want to have a successful simulation, we need contact history output variables of CDIS. So we have to turn on the history outputs for both of our steps. So let's cancel the simulation run, go to the history outputs, double click, add a contact output. Now here you could, if you had multiple contacts in the model, select for which contact in your model you want to save the required results. We have only one, so there's no hard choice here. We go to the variables output, and instead of contact forces, we'll turn on CDIS. This is the relative contact displacements. So only relative contact displacements are needed for the wear simulation to work. We confirm this setting by OK, and we need this history output in both of our steps. So we'll just right click and propagate our history outputs in the second step, or to the second step. Now we will run our simulation and overwrite the existing results. After the simulation finishes, we can take a look at the results. Now the movement of the pin and the displacements and stresses are the same as previously. We only got some additional fill variables. You can see here that we have like sliding distance, surface normal, wear depth, mesh deformation, and combination of the displacement, of mesh deformation, and of the wear depth. So we have like a combined field. Now what they are showing us, the sliding distance is something that goes into the Arcart equation and is the distance that is the relative displacement between the master and the slave surface. Then we have a surface normal. This is the vector that shows you the shape of your surface, so the normal direction of the contact surface. And then we have the wear depth, and this is something that we are interested in. So the wear depth is the computed depth that our simulation evaluated. This is a vector which has 3 components and a magnitude field that we can take a look at. So let's try to animate this wear depth to see what is happening. So go to the beginning of the simulation. First we have a compression, and then we start to move in the step number 2. So this is step number 2. And while moving in this step, we see that the wear is computed and wear is accumulated in the material. When the pin is going back, the wear is increased. And this is everything is happening in one simulation cycle. Now the mesh is not deformed here during the simulation, only the wear is computed. But we can see how this wear affects the mesh, the deformation, the geometry, so that we plot it instead of a deformation variable and displacements. So instead of displaying or using displacements to deform our mesh in the post-processing, we can use wear depth to deform our mesh. So if we double-click the legend, go to post-processing, and instead of displacements, we select, for instance, wear depth, and OK. Now I will have to zoom in a little bit in order to see for you to see the change. Something like this maybe. And when I now move the slider, you have to look very careful, but because the values of the displacements are very small, but when you change the time of the simulation, you will see that the top surface of our model is deformed, and it deforms towards the material. So the deformation is occurring on these nodes which were computed. The one thing that will happen now is that we have to repeat this simulation, so in multiple cycles, and it works in such a manner that first one cycle is computed and no mesh deformation is happening during the one cycle. So this is just a visualization how it would look like at the end of the step, but nothing is actually changing the mesh in during the cycle. But after the cycle is finished, the wear, as we see it now, so this wear is computed. It is used to deform the starting mesh, so the mesh that we started with, and the second cycle of the wear simulation is run on this already deformed mesh. We'll try to do something, so the simulation that will show this setup or this continuation of the wear development. So we'll go to the model setting in the model tab, and we will increase the number of cycles to a value of 3. We'll change nothing else, we'll just run the analysis again. Now for the first time, the simulation had more than one cycle, and I will just for the second close the monitor window after the simulation finished. So I will not load the results, I will just close the window, and you can see that in the output part of our software, we have a output where when the cycle number 1 was started, cycle number 2 was started, and cycle number 3 was started. So after everything is okay, all the cycles were computed successfully. We have a finished simulation. So now by opening the monitor again, the monitor window, and selecting results, we can load the results for the 3 consecutive wear cycles. We can animate and show how the wear progresses. So I will just show the wear using the colors, so the field output variable. I also have the formation variable, wear depth, so I can see it. But now I will not be able to see the movement of the pin. So because I'm only showing using wear to deform the mesh in post-processing, I cannot see the movement of the pin. I will change that, so double click on the legend, and on the post-processing settings I will use the vector, the summed vector, which will combine displacements, wear depth and mesh deformation in one field. So I will use this setting in order to see everything that's happening with my mesh, and I will try to animate this result to see the evaluation of this wear process. So we go first time to the right and back, and we can see that the wear is building up, and then we have another cycle going again to the right and back, and the third cycle going to the right and back. Now we can also see the movement of the pin. We can see the deformation of the mesh, and we can see also the value of the wear. Now there is a limitation of this current setup, and the limitation is the thickness of the first element under the surface. Because the mesh is deformed by wear, it can happen that the nodes on the surface are pushed towards the nodes which are inside the material, and it can happen that the material, the finite element, is deformed using because of it. So deformed in the sense that it's not usable anymore. So it can happen that this node moves towards the node which is on the other side of the finite element, and the volume of such an element is negative, and you cannot use it for the computation. And that is why you would like, or we would like, that when the wear is applied, so when the deformation of the slave surface happens, it also translates to other nodes in the material. So, and this is the last setting that I'll talk about. So if we open up again the settings for the FEA model, And we can see here that we have a setting for the mesh deformation. This means that after the first cycle, when the surface is worn down, so the nodes are pressed towards the material, not only the surface nodes are deformed, but also the nodes which are connected to them. So this is used by the so-called boundary displacement method, and it enables to compute wear with larger wear depths and with multiple wear cycles. So I'll just turn this setting to yes to show you the difference. I'll confirm by OK and run the simulation again. After the simulation is finished, I can take a look at the results. And if I just output or plot wear depth, I will see no difference because on the surface everything is exactly the same. But if I take a closer look at the nodes which are one layer lower than the surface nodes, so these are the nodes beneath, so the finite element nodes beneath the surface, and if I play around with animation, I can see that the nodes are first in a line, and then after one cycle, when the mesh deformation actually takes place, the nodes are pressed downwards. So the shape of the finite element is kept much better than when those nodes to the inside of the material are just not moved, so if they remain fixed. Now, we know every setting that we can choose to set up our wear simulation. The last thing that we have to do, according to our assignment, is to increase the number of cycles to a value of 10. So let's go back to the FEM model, edit the settings. Now I will select 10 cycles. I will also decrease the number of results. I don't need now anymore to see the movement of the pin, all the increments between the first and the last time step. So I will just output only the final result of one wear simulation, one wear cycle. So the final wear values will be saved, and the field values will be saved, and I can then at the end see only 10 different results. In order to get a little better and a little smoother result, I will also change the setting of the step so the step where I defined the incrementation, and I will reduce this value to 1 to 5. So this is like I will try to increase the number of intermediate steps. I will not save the results in them, but using a smaller time step, I will get a better distribution of the wear on the surface. So now I will run the analysis for the last time. So after the simulation finishes, this time it took a little bit longer because we had to compute 10 wear cycles, but we can load the results. And if we take a look at the step and increment drop-down menu, we see that we have only a couple of results. And this is the result at the beginning. And then after, I will turn on, let's say, wear depth. And then we have the result at the step 2 and increment 80. So this is the end of the first cycle and then end of the second, third and cycle and so on. Because we turned on, so I'll go to the last one, because we increased the value of so decreased the time step size, we got a much smoother distribution now of the wear depth, and the results look much better. If we take a look at the from the side, we see that it's very evenly distributed. on the plate, and the values are um, so very similar at the beginning and at the end of this path that the pin is taking, um, sliding at on the plate. Now the final thing that we'll like to see as a result is probably how, let's say, the wear depth developed for one material point, for one node. So we'll go and create a new history output by double-clicking the history output. We'll select the field that we would like to output. This is the wear depth, but we're maybe not interested in the magnitude of the wear depth vector, but we would maybe like to see the just the y direction, so the second direction of the vector, h2, and we have to select a part of the geometry. Now I will select only one node, and that is why I will use the option more and node. I will select one node here in the middle of my wear path. Confirm by OK. In doing that, I created a new history output. I can open up now my history output, H2, double click, select all the values, right click and select plot. What I'm seeing here is the development of the wear depth when it started at 0. So at the time 0, the wear depth was 0, but I'm missing 1 point here. So the output is missing the first value, so the 0 value. But then the wear step in my case developed as the curve suggests. Now, what is now time 20? So we said that the whole procedure should take 10 seconds. Don't forget we used 2 time steps to model one cycle, and the duration of the first time step equals 1 second, duration of the second time step equals 1 second. So the combined time at the end of our wear simulation is 20 seconds. With this, I will conclude this tutorial about how to perform wear analysis inside the PrePoMax.